Hello, everybody. Excuse the crickets and nature sounds. It's nighttime and I'm outside, kind of enjoying the weather. It feels nice. But today we're going to talk about some techniques that mathematical physicists use. One of them is working with basically the structure of the space of physically equivalent motions. And why you would be concerned with this, by the way, this is the second episode of our series. Why we would want to work directly on that space is because conserved quantities, we can reduce the equations of motion if possible, to simplify them, and also get scaling laws without these ad hoc kind of constructions, but getting them from fundamental principles. So let's look at a particle in R3, where phase space M is the cotangent bundle with canonical coordinates QI, PI, and symplectic. Let's say symplectic form. So the symplectic form would be omega, summing over the three, indexing the three space dimensions. Now, what we can do is define an infinitesimal rotation that is in the Lie group, and how it acts on the entire physical state by QP mapping to some rotation matrix acting on Q and rotation matrix acting on P individually. What we can do is write an infinitesimal rotation. Sorry, not R3, or epsilon. Sorry, my brain, I just had like an aneurysm. What the heck? But we can write this as the identity matrix plus some epsilon times some C here, plus some higher order terms in epsilon squared, where this C hat V could be equivalent to C cross V, and C itself is in the, trying to make this fancy, is in the Lie algebra for SO3 that is isomorphic to the real numbers. Okay? So it's an element of the Lie algebra. It's basically a symmetry generator. And the vector field generated by this symmetry, where basically it's a vector field on M, on the cotangent, on the phase space, generated by this 3C cross Q I, and here's our generators, dp I. Alright, so that would be the vector field itself, and from the vector field we can contract the vector field with the symplectic form. And so let's say iota of Cm contracting with the symplectic form would give us Z cross QI dpi, just by how symplectic forms interact with the bilinear. And then if we go through, we know that by vector identity, we can take the let's see. We can dot this with Q cross dp plus C, the Lie algebra generator, cross dp, with this dotted here, Q plus, this should be cross dp. And remember, we're in 3 dimensions, so the cross product's pretty nice. It's a good thing. And then we can have the differential of Q cross P here to be equivalent to the differential of C dotted with Q cross P, just simply because we can take the differential out and define something called J sub C, where it's this quantity here. So we'll just say C dot Q cross P. And what this quantity is, well, first of all, what we have here is that the vector field is iota C on the phase space. The contraction of the vector field with the symplectic form allows us to have a generating function, or it's the derivative of this generating function here. It's the derivative of the momentum map for the rotation. And if we choose a basis, let's say, if we choose a basis for C, let's say EX, EY, and EC, or EZ, then that will yield 3 components of the angular momentum. So we would get some L. The angular momentum itself would be Q cross P. That is LX, LY, and LC. All right. Now, basically what this allows us to do is rotate a whole experiment and move the state along the vector field. And the symplectic form basically is asking us what function generates that exact flow. And the answer, of course, would be it would be the epsilon dot with the angular momentum. Now, angular momentum is not just something that's conserved by rotation. The angular momentum is the Hamiltonian generator of the rotation itself. And so this is the geometric statement of Noether's theorem, that a continuous symmetry direction here corresponds to some conserved quantity, J sub Z. All right. Now that we have the basic idea of the rotational symmetry and the momentum map, and how it depends on Noether's theorem, we can now constraint itself, which we talked about last episode. Constraints and restrictions onto this space are then going to allow us to reduce the space of motion from the ambient space. So we can attach a particle to some massless rod, let's say massless rod of length L, okay, just for argument's sake. And how we would choose to measure L is just Q dot Q to give us L squared, part of the distance. And the configuration space is therefore going to be the two-sphere. Q of S2. And a level set of f of q being q dot q. And so we're just going to work simply on this physical subspace, all right, with a rod of length L, all right? Now, if we take the constraint and we differentiate it, we'd be left with this, which basically tells us that it implies that dq dot dq dot should be equivalent to 0. So the physical tangent bundle on this phase space for a rod of length L, with being on a sphere, the tangent bundle, or the physical tangent bundle, is just going to be q v R3 cross R3, given that q dot q is equivalent to L squared, and that q dot v is equal to 0. All right, and now the particle exists only on the sphere, and its velocity is always tangent to it. All right, so now that we have this, so the particle is, sorry, I'm visualizing the system wrong. We are attaching a particle to this massless rod itself of length L. All right, and so the particle is attached to the rod. Okay. And this rod is L itself. All right. Well, yeah, let's go for that for now. Now what we can do is choose spherical coordinates, because we're just choosing a basic, the coordinate of the particle would give us, sine for the x component would be this, for the y component it would be this, and then for the z component it's this. Now the ambient Euclidean metric that we have, we're restricting it to sine, just as we did in the previous episode, but the kinetic energy would be 1/2 ml squared times the polar velocity times this azimuthal velocity here squared, and with uniform gravity, let's say v is equal to mgl cosine theta, taking the vertical upward, that vertical polar angle, the constrained Lagrangian is going to be 1/2 ml squared, polar velocity squared, sine squared, azimuthal velocity squared minus mgl cosine theta. And the equation of motion that survives the symmetry is going to look like theta dot minus sine squared, or sorry, sine cosine azimuthal dot squared plus g over L sine theta is equivalent to 0, and the derivative of ml squared sine squared this, sorry. That should be equal to 0. And the conserved quantity becomes precisely the vertical component of that angular momentum. So, taking this, we'll be left that the momentum here, or this conserved quantity, is this vertical component, sine squared azimuthal angular, sorry, the azimuthal velocity, the LZ. This is a constant. So that LZ component, the full rotational symmetry of the free space here, right? The rotational symmetry is kind of broken by gravity of this rod, but the rotation around the axis, around an axis, remains a symmetry. So, or sorry, the z-axis here, that is a symmetry. So it survives as a conserved charge. This P right here is a charge itself. It's a Noether charge. And the constraint will remove that radial direction so that the remaining symmetry is basically selecting what cannot change, which is the LZ component. Now, if we step away from some pendulum, right, just looking at a spherical pendulum, what we can do now is look at a general system. So let's say we have MQ double dot is the gradient of a potential here, where the potential is homogeneous. So we can, that basically means we can write that this potential scales by lambda from the inside, that we can write it to degree k in general. By the scaling symmetry, we know that u of lambda q should be equivalent to lambda k minus 1 of the gradient. If we take the gradient of this, we, by the chain rule, this would have to be true. Now suppose Qt is a solution. What we can do is rescale the trajectory. So Q prime, T prime, should be equivalent to this scaling parameter, lambda, times Qt. And T should be some mu times T. Now if we do that, this left-hand side will scale as the second derivative of the coordinate prime in this transformed system to be lambda over mu squared times q double dot. And for q prime to satisfy the equation of motion, what has to happen is that lambda over mu squared is equivalent to k minus 1, which means that mu squared should be equivalent to lambda times 2 minus k, or mu basically is just lambda times 1 minus k over 2. Now, the characteristic time scale then, this characteristic time scale will be proportional to a to the 1 minus k over 2. Now, if we were to say, well, let's look at the inverse. Let's go over here. Let's look at the inverse distance potential. So, basically saying u of r is proportional to 1 over r. Alright, just inverse to the distance. We have that k is equal to 1, right? Or sorry, negative 1 in this case, because it's 1 over r. So mu is going to be equal to lambda of 1 minus negative 1 over 2, which should be equal to, lambda should be equal to 3 halves, which tells us that t should be alpha over 2 halves, which implies that t, the characteristic time scale, should be proportional to a cubed. This is Kepler's third law. We just derived it without solving any orbits. It's basically just Kepler's third law can be derived as a direct consequence of the homogeneity of the inverse distance potential, which is the gravitational potential, and the scaling symmetry of the equations of motion. So, changing the basically, if you change the size of the system, that alters the forces in a very predictable way. And a clock, the characteristic timescale, says that the clock must slow down or speed up exactly to the right factor that preserves Newton's equations. So for gravity, a large orbit will feel like this weaker force that is basically a required slowing will give us that the characteristic time, or the period squared, should be proportional to A3. Okay? Now, what this allows us to do is just look at the space of possible, in mathematical physics, what you do is you take the physical idea, or the whole thing to take away from this is that you want to study the space of physically possible states first, then write the dynamics on it. Okay. So you want to restrict, you want to have some constraint to restrict some configuration space to a level set, or on a sphere, and looking at the tangent velocities and how they are constrained. And what this does is it introduces a induced metric, and this is the geodesic part of the dynamics. That's kind of what you get yielded out of this. If you look at symmetry, how symmetry plays a role in the Lie group action on the cotangent bundle and contracting the vector field with the symplectic form, you will find that the conserved momentum map, or basically it yields a conserved momentum map that allows you to describe the sets of conserved quantities that appears directly here. Alright? And then finally, just looking at homogeneous potential in general, and using some kind of argument of similarity transformation that yields scaling laws like Kepler. There's also other scaling laws that you could get, like isochrony, etc. So there's just ways of organizing the equivalence, basically organizing the equivalence classes of motion. Okay. under the relevant transformations. All right. That's the main goal of this episode, is just to think about that. And the spherical pendulum really illustrates them all together. You have a rod that constrains a position to S2, and then to its tangent planes, and the rotational symmetry about the vertical axis will generate this conserved quantity. And if the force is homogeneous, like as a linear gravitational potential, the scaling lengths and the rod length will produce a family of dynamically similar pendula, linking the period of it to the length. And deeper still, you can still think about the momentum map, constraint reduction, and like these scaling ideas as manifestations of the same geometric strategy. You want to really identify, it's the job of the mathematical physicist to identify the minimal structure needed to describe the system, then use invariance to simplify the equations before solving them. All right? That's really the heart of thinking about mechanics in a modern way. It's just using geometry and symmetry to compress the complexity of the motion into its essential conserved one. All right, thank you guys for watching, and I'll see you next time.